Hydroelectricity is the term referring to electricity generated by hydropower, the production of electrical power through the use of the gravitational force of falling or flowing water. It is the most widely used form of renewable energy, accounting for 16% of global electricity generation, 3,427 terawatt-hours of electricity production in 2010, and is expected to increase about 3.1% each year for the next 25 years. Hydropower is produced in 150 countries, with the Asia-Pacific region generating 32% of global hydropower in 2010. China is the largest hydroelectricity producer, with 721 terawatt-hours of production in 2010, representing around 17% of domestic electricity use. The cost of hydroelectricity is relatively low, making it a competitive source of renewable electricity. The average cost of electricity from a hydro station larger than 10 megawatts is 3 to 5 US cents per kilowatt-hour. It is also a flexible source of electricity since the amount produced by the station can be changed up or down very quickly to adapt to changing energy demands. However, damming interrupts the flow of rivers and can harm local ecosystems, and building large dams and reservoirs often involves displacing people and wildlife. Once a hydroelectric complex is constructed, the project produces no direct waste, and has a considerably lower output level of the greenhouse gas carbon dioxide than fossil fuel-powered energy plants. History. Hydropower has been used since ancient times to grind flour and perform other tasks. In the mid-1770s, French engineer Bernard Forest de Bellador published Architecture hydraulique, which described vertical and horizontal axis hydraulic machines. By the late 19th century, the electrical generator was developed and could now be coupled with hydraulics. The growing demand for the Industrial Revolution would drive development as well. In 1878, the world's first hydroelectric power scheme was developed at Cragside in Northumberland, England by William George Armstrong. It was used to power a single arc lamp in his art gallery. The old Shirlscoff Power Station No. 1 near Niagara Falls in the U.S. site began to produce electricity in 1881. The first Edison hydroelectric power station, the Vulcan Street plant, began operating September 30, 1882, in Appleton, Wisconsin, with an output of about 12.5 kilowatts. By 1886 there were 45 hydroelectric power stations in the U.S. and Canada. By 1889 there were 200 in the U.S. alone. At the beginning of the 20th century, many small hydroelectric power stations were being constructed by commercial companies in mountains near metropolitan areas. Grenoble, France held the International Exhibition of Hydropower and Tourism with over 1 million visitors. By 1920, as 40% of the power produced in the United States was hydroelectric, the Federal Power Act was enacted into law. The act created the Federal Power Commission to regulate hydroelectric power stations on federal land and water. As the power stations became larger, their associated dams developed additional purposes to include flood control, irrigation and navigation. Federal funding became necessary for large-scale development, and federally owned corporations, such as the Tennessee Valley Authority and the Bonneville Power Administration, were created. Additionally, the Bureau of Reclamation, which had begun a series of western U.S. irrigation projects in the early 20th century, was now constructing large hydroelectric projects such as the 1928 Hoover Dam. The U.S. Army Corps of Engineers was also involved in hydroelectric development, completing the Bonneville Dam in 1937 and being recognized by the Flood Control Act of 1936 as the premier federal flood control agency. Hydroelectric power stations continued to become larger throughout the 20th century. Hydropower was referred to as white coal for its power and plenty. Hoover Dam's initial 1,345 megawatts power station was the world's largest hydroelectric power station in 1936. It was eclipsed by the 6,809 megawatts Grand Coulee Dam in 1942. The Pico Dam opened in 1984 in South America as the largest, producing 14,000 megawatts, but was surpassed in 2008 by the Three Gorges Dam in China at 22,500 megawatts. Hydroelectricity would eventually supply some countries, including Norway, Democratic Republic of the Congo, Paraguay and Brazil, with over 85% of their electricity. The United States currently has over 2,000 hydroelectric power stations that supply 6.4% of its total electrical production output, which is 49% of its renewable electricity generating methods. Conventional most hydroelectric power comes from the potential energy of dammed water driving a water turbine and generator. The power extracted from the water depends on the volume and on the difference in height between the source and the water's outflow. This height difference is called the head. A large pipe delivers water from the reservoir to the turbine. Pumped storage. This method produces electricity to supply high peak demands by moving water between reservoirs at different elevations. At times of low electrical demand, the excess generation capacity is used to pump water into the higher reservoir. When the demand becomes greater, water is released back into the lower reservoir through a turbine. Pumped storage schemes currently provide the most commercially important means of large-scale grid energy storage and improve the daily capacity factor of the generation system. Pumped storage is not an energy source, and appears as a negative number in listings. Run-of-the-river hydroelectric stations are those with small or no reservoir capacity, so that only the water coming from upstream is available for generation at that moment, and any oversupply must pass unused. A constant supply of water from a lake or existing reservoir upstream is a significant advantage in choosing sites for run-of-the-river. In the United States, run-of-the-river hydropower could potentially provide 60,000 megawatts. Tide. A tidal power station makes use of the daily rise and fall of ocean water due to tides. Such sources are highly predictable, and if conditions permit, construction of reservoirs can also be dispatchable to generate power during high demand periods. Less common types of hydro schemes use water's kinetic energy or undammed sources such as undershot water wheels. Tidal power is viable in a relatively small number of locations around the world. In Great Britain, there are 8 sites that could be developed, which have the potential to generate 20% of the electricity used in 2012. Sizes, types and capacities of hydroelectric facilities. Large facilities. Large-scale hydroelectric power stations are more commonly seen as the largest power-producing facilities in the world, with some hydroelectric facilities capable of generating more than double the installed capacities of the current largest nuclear power stations. Although no official definition exists for the capacity range of large hydroelectric power stations, facilities from over a few hundred megawatts are generally considered large hydroelectric facilities. Currently, only 4 facilities over 10 gigawatts are in operation worldwide. See table below. Small hydro is the development of hydroelectric power on a scale serving a small community or industrial plant. The definition of a small hydro project varies, but a generating capacity of up to 10 megawatts is generally accepted as the upper limit of what can be termed small hydro. This may be stretched to 25 megawatts and 30 megawatts in Canada and the United States. Small-scale hydroelectricity production grew by 28% during 2008 from 2005, raising the total world small hydro capacity to 85 gigawatts. Over 70% of this was in China, followed by Japan, the United States, and India. Small hydro stations may be connected to conventional electrical distribution networks as a source of low-cost renewable energy. Alternatively, small hydro projects may be built in isolated areas that would be uneconomic to serve from a network, or in areas where there is no national electrical distribution network. Since small hydro projects usually have minimal reservoirs and civil construction work, they are seen as having a relatively low environmental impact compared to large hydro. This decreased environmental impact depends strongly on the balance between streamflow and power production. Micro hydro is a term used for hydroelectric power installations that typically produce up to 100 kilowatts of power. These installations can provide power to an isolated home or small community, or are sometimes connected to electric power networks. There are many of these installations around the world, particularly in developing nations, as they can provide an economical source of energy without purchase of fuel. Micro-hydro systems complement photovoltaic solar energy systems because in many areas, water flow, and thus available hydropower, is highest in the winter when solar energy is at a minimum. Pico hydro is a term used for hydroelectric power generation of under 5 kilowatts. It is useful in small, remote communities that require only a small amount of electricity. For example, to power 1 or 2 fluorescent light bulbs and a TV or radio for a few homes. Even smaller turbines of 200 to 300 W may power a single home in a developing country with a drop of only 1 meter. A Pico hydro setup is typically run-of-the-river, meaning that dams are not used, but rather pipes divert some of the flow. Drop this down a gradient, and through the turbine before returning it to the stream. Underground. An underground power station is generally used at large facilities and makes use of a large natural height difference between two waterways, such as a waterfall or mountain lake. An underground tunnel is constructed to take water from the high reservoir to the generating hall built in an underground cavern near the lowest point of the water tunnel in a horizontal tail race, taking water away to the lower outlet waterway. Calculating available power. A simple formula for approximating electric power production at a hydroelectric station is: where is power in watts, is the density of water, is height in meters, is flow rate in cubic meters per second, is acceleration due to gravity of 9.8 meters per square second, is a coefficient of efficiency ranging from 0 to 1. Efficiency is often higher with larger and more modern turbines. Annual electric energy production depends on the available water supply. In some installations, the water flow rate can vary by a factor of 10 to 1 over the course of a year.